Sounds great. Thank you, Ken. And hello, everyone. Welcome again. It's great to be back, as always. Today, we are going to go over the vegetation change notebooks, and also want to welcome everyone to the new Cape Town transition for the Digital Earth Africa Data Cube. It has been quite an effort, I understand, getting that transferred over. It's a little slower for me since I'm on the other side of the world, but I think for you all, or at least those in the African continent, should be much faster now, hopefully. Also wanted to point out, well, actually, I guess let me go ahead and share my screen. Actually, my sandbox has already started, but I did want to point out in the bottom right-hand side of the sandbox, when you first log in, there's a little feedback section. So if anyone has any issues, comments, questions, concerns about anything in the sandbox, feel free to just go there and fill out the form, and I'll go to our help desk and our engineers, and it'll be resolved, or even our technical or business staff, as a whole. So great news there. So can everyone see my screen?
Yes,
we can.
Yes.
Yep. Great. Okay. So just wanted to put together a couple slides. Again, the topic overall is just on the specific notebooks for vegetation change. And vegetation change as a whole is pretty simple. The notebooks go through a little bit of statistics to actually generate some of the images that give us a little bit more information about changes in a particular area. But overall, the notebooks kind of work on two types of band math, or one or the other, one being NDVI and the other being EVI. NDVI is very common. I would assume that a lot of people have probably seen that index in other notebooks. It's very useful. And again, it's just basic band math. So we're just taking, near infrared minus red over near infrared plus red, and then that product is NDVI, or the normalized difference vegetation index. The other option in these notebooks is using what's called the enhanced vegetation index, EVI, and you can see in the middle of the screen there the band math formula for producing that index. And it's a little more complicated, and it's a little more useful for determining changes in heavily forested areas, or areas where there's already like a lot of green, or minor differences that might be more difficult to see with NDVI. So if there's a region in particular that is of interest to see changes, and you don't see a whole lot of changes, again, especially in like forested areas, you can switch over to EVI and maybe extract just a little bit more statistical information about that region. Wanted to also point out that the platform available currently for vegetation change in the notebooks or sandbox is Landsat 8, and it covers all of Africa. And we have only years from about 2013 to about 2021 currently in the notebooks. I would suppose that it's very feasible to perform these calculations with other types of platforms, but the high-level notebooks that we'll go over are using Landsat 8. And again, this data is accessible in Explorer, which I can show if anyone's interested. And of course, all these little squares in here are each of the tiles, and you can actually go and click on each of those if you want to learn more about that specific region and the data available there. So that being said, we can jump straight into the notebooks, and let me share, let me make sure I have the right ones here. Made a copy as well, so I'm going to get a shareable link. I'm going to put it in the chat for anyone who would like to follow along. And if you're just fresh logging in, you may have to sign into your account to be able to see that notebook. Nevertheless, so let's go all the way to the top here. And we'll just run through this notebook kind of line by line and talk about it, and we'll run some specific areas. And in the meantime, if anyone has any specific regions of interest, I believe, Ken, you had mentioned one that we can go over, but if there are any other regions with small areas that we can look at, just put it in the chat and we can take a peek around there here shortly. So overall, again, want to point out that the product used for this notebook specifically is the Landsat 8 surface reflectance product. And overall, you know, so we're after kind of this cloud-free Landsat 8 imagery. And as we go through this notebook, and as you may find yourself, if there are ever any errors, even potentially CRS errors, that could be because there is either no data or too much occluded imagery due to clouds in that region. So you may just want to change around your dates and things of that nature. Overall, we're calculating indices that indicate vegetation, and we do that with NDVI or EVI, and we perform some additional statistical math to give us some kind of binary or more clear descriptions visually of whether or not there's actual change in a particular region. And, you know, also, I guess before we get too far into this, I do also want to point out a small tool change, because we'll get into this later in the notebook. I think this is new since the Cape Town change, but at the high level in the notebooks, I do want to point out here, so originally this script directory contained a lot of functional scripts usable in a lot of the notebooks. And if you go in here now, you will see this warning sign that these have been deprecated, meaning that they're no longer in use. They've been since updated, and the updates are now under Tools. And there's a few more options in here, and those specific scripts now are under DEAfrica_tools. And we can see here, if we go to the data handling .py, we have a little bit more going on in here, and some more details on actually what's happening. So if there are any questions about some of the specific tools being used, make sure you're looking at the tools, DEAfrica tools directory, and not the scripts directory. I think everything in the scripts directory now is deprecated and now being handled under these new tools. So that being said, if we go back here to our vegetation change notebook, everything in the first block is pretty typical to what we would see in the loading of a new notebook. We want to import our data cube. It's very important. We use matplotlib for getting a lot of our plots, NumPy, Xarray for handling all the data as usual, and some of these DEAfrica tools, as I pointed out now, for data handling, the band indices, and the plotting. We also use this utility here, which is a processing tool, but a little irrelevant if you don't need to go into the details there. And let's just go ahead and run through this. I think this notebook, so I did poke around. So this is the stock notebook here that we'll take a look at first, and we'll just make sure it runs. And I do have another example pulled up for a region in Sierra Leone. And if I do recall, Ken, you may have to remind me of the preserve you had mentioned, but we can get to that in a moment. Nevertheless, let's go ahead and start through here. So we'll start our first cell, and I'm going to keep the regions fairly small here, since I am on the other side of the world from the data center. It does take a little bit longer for me to process larger areas. We're going to load the data cube change detection application here. Just hit enter. It gives us some information about where it's being called from. So the next step, we choose our analysis parameters, and they're pretty simple. We've got our latitude, longitude, our buffer, our time range, and our time baseline. And latitude and longitude are pretty self-explanatory, and that is the center point for which we want to look at. And the buffer is the number of degrees around the central point that is being loaded. So the smaller the buffer, the smaller the area. The larger the buffer, the larger the area. Really around 0.1 is pretty average size for the data cube to manage with its given resources for a typical account. Excuse me one second. I have loaded successfully up to 0.2, but it almost maxes out the memory depending on the process. So you can just keep an eye on that. Actually, down here in the bottom left-hand side where it says memory, it'll actively show you the engagement with the notebook. So if you're loading too large of an area, you can see there if it's getting up to the maximum size, and you may want to reduce your buffer just a little bit. Down here in the time range, this is the full set of dates that are going to be processed for the sample. And then the time baseline is, oh, we got a file saver. The time baseline is the comparative date from the original date here that will be displayed, and I can show you that in a moment. So again, these are just the stock values. We'll just run this. We're going to look at the map here, and something kind of interesting that I discovered is that if there's a particular area that is of interest, you can also just kind of go through this display map function, and say we wanted to look a little bit to the right. If you double click on the map, it'll actually show you your latitude and longitude, so you don't have to go back and forth between applications to find your lat and long. If you just want to do something kind of quick, you can just use this map function, and it's fully interactive. You can zoom in and out, and double click, and we'll get our lat and long. It'll update the resolution just a little bit, and you can go ahead and plug that in up above. So we do have our region here. Let's see where it is. Let's pull it back out just a little bit. Oh, looks like it's being slow. Nevertheless, we'll maybe let it think about that. Let's see. So I think we're near Nairobi, I guess. I don't see the exact boundaries there. Nevertheless, we're in West Africa. So we'll continue down here. And here we're going to actually query the data from the data cube and load it with these functions, all very standard between the notebooks. So I'm gonna hit run there. And we'll see down here this output, kind of just make sure that it's telling us that things are good in terms of loading. And it tells us that it's rescaling, and that it's loaded 48 time steps, and we have at least 70% good quality. And that's also defined. I want to point that out here. So this min good data is an important function for querying and filtering data based on the quality of the pixels, and the QA is a standard layer in a lot of the satellite imagery. And it's more often the quality index is typically a factor of cloud cover, though there can be other features that can dictate good data in the eyes of the data cube there, which can include snow or features that look a lot like clouds, or kind of single color regions, that might be mistaken as a cloud. But typically 0.7 is an average number that the data cube uses to filter data in that regard. So we're just going to print that and see our coordinate system, our data variables, and our attributes for projections. Also wanted to point out, for some of us, it's a little easier to read. If you actually just do DS, it kind of puts it in like a little bit more of a table, which you can see some other factors with. All preference, thought I'd point it out. So now we're actually going to plot the time steps. And these two values here are the factors that set the system to show the steps in this plot. And sometimes I think it happened in this other notebook I'll show. But if you get an error out from this, typically the best thing to do is just play around with these time steps and bring it into a more viewable region, if you will, and it'll display the output here. So now we're going to be doing the computations, and this is where the NDVI or EVI choice comes in. It gives a little bit of a description again of what those two indices are. And then this is where it's actually applied in the notebook. And it's very nice because you can actually just kind of copy and paste the code. Right now, the notebook's set up for NDVI. But if you want EVI, all you have to do is just copy and paste that down into this box here. We'll just keep running with it as NDVI. Looking good. So now we're actually going to plot the data in red, yellow, green colorization with our time steps and the given index. And as you can see up here, we have two dates for comparison. We have one in 2013, one in 2017. And it looks like there's some change here, but we don't really still know quantitatively how much change there is. So now we're going to do the statistics in the notebook. There's a nice description here of what's actually happening. And it's basically just doing some really basic things, comparing the pixels to different dates and kind of just saying, is it more here, is it less here? What's changing? This is actually this and the following script here are actually what are composing the statistics for the map itself. So we'll just make these samples, we'll run this. It tells us here the number of observations. And then we're going to actually produce the test here. And it's taking our data here, telling us what it's doing. And now we're going to visualize it. And there's some details here about how it is actually being visualized. We can set the significance level. Talks about, here we go, it's going through the identity of the difference of the mean, it's classifying it. Let's see, let's run that one. And then we're going to actually construct the comparison plot here from the previous math that was performed. Oh, maybe I didn't run this. Stand by. Let's try it again. Looks like it's running. Okay, so now it's produced the baseline mean composite and the post-baseline composite. And up here, I just want to point out, if you just look at the maps, the importance of using this is that with some very basic statistics applied through the notebooks, we can extract things that we may not see. I mean, up here in a couple spots, we see, some different colors and things, but there's no real way to quantify that. So down below, we actually get the quantification from the notebook on where those changes are. So this is all the statistically significant change in the map. And then this bottom right picture is the statistically significant deforestation in that region. And if we wanted to, we could look at certain regions here and even extract this and run further statistics if we wanted to build a little bit more out into the notebooks. And here is where it's actually quantified. So we can say 7.101% of pixels likely underwent significant change, and 5% of pixels that likely underwent deforestation in this case. And I just want to keep in mind that while this is a very good indicator, it is not always completely accurate. I did notice in a couple areas that I ran this on, roads are a factor of change, which could include deforestation, but without necessarily knowing the dates for which roads were constructed, there could be some environmental factors that can give some false flags in that regard. So also want to point out this cog writing tiff function. So if we want to acquire the data, it's just as simple as running that. And we'll see over here on the left-hand side that we now have a tiff in our directory where we can actually right-click on that and hit open in browser. And then we're going to get a little download here in the bottom left-hand side, which is the actual tiff image. And if we wanted to pull that out and do additional processing or use it in a paper or something of that nature, this is the image here, which is a great new function. I think this was broken previously, so it's nice to have this now. And then that's pretty much it as far as the notebook's concerned. Wanted to point it out. Let's see, one area here in Sierra Leone that I thought might be area of some potential deforestation, and it just all ran the same thing in the notebook with the exception of the EVI. So this is a case of an EVI calculation, and a lot of times you may not necessarily see a lot of change, but again, it's good to run an EVI index in heavily forested areas to see kind of smaller changes. So again, all the same functions for the most part in here, with the exception of different data. And let's see, what dates was this for? So we're looking at 2014 and 2018. It's really not that much, but you can see in a rather densely forested area, it does extract quite a lot of points there of flag change, which could be actual deforestation. It could be due to natural causes of forestry, dying in an area, what have you. But nevertheless, it gives you a great visualization of the specific regions where, if you were to just look at these maps, there'd be almost no way to extract each and every one of those points, especially on large areas. So it's a very handy tool for doing so. I think that's pretty much it there. I see we're running a little bit on time. Ken, do you want to run another sample area?
I think this is a great presentation, and we could have a proposal from one of the participants in the room so that it's more inclusive based on their local knowledge.
Sounds great.
Volunteer, Stephen, Corey, Stella, Eric, Edwin, Eileen. So put in the Latin long in the chat, please, if you have somewhere you want us to look at. Thank you.
Hi, Ken.
Yes.
Yeah,
Welcome.
I have an area. I'm trying to get it there. The Brim River. That is where we have some of the same areas destroying the banks of the rivers for some time now. I'm trying to get some coordinates for you. So just in a moment, I'll get some coordinates so that we see what has happened over a period of time.
Thank you, Eric. You mentioned which river? Ankoba.
Brim River, the Brim.
The Brim.
Brim River. Let me just copy.
I'll stand by for those coordinates. I did run a few spots in the, it's pronounced the Neokolokoba. Is that correct, Ken?
Nyokololoba. It's a very, it's a Senegalese name. It's quite a park which had a lot of issues with deforestation.
Do you know of any particular areas in that park? I searched a little bit around the central area here where the actual, like right around this marker in a block. I really didn't see too much change, but we can always expand a little bit more. Let's take a look at the Biram River.
Area.
Okay.
So yeah, these are the coordinates for Brim River from Eric Mwala. I've looked at Google Maps.
Let's take a peek. Perfect. 5. Perfect. Thank you for those coordinates. Let's go ahead and plug that in here and see what we get. So we got our latitude and our longitude. I'm going to keep this extent small for now, and we'll see what we get into our buffer size of 1. I'm just going to run this from the beginning just in case. And we'll keep the same date range and see what we get here. And let's display it on the map, make sure we have the right area. That looks, it's in Ghana. That's a start. So we'll go ahead and keep running down here. And again, with the 0.1 buffer, the processing time is very quick. So just for a quick check in an area before you load the system down, it's a good size to work with. So we're counting pixel quality, and it's going to be acquiring the slices for that. I do want to point out again that if there's ever a CRS issue specifically, it could very likely be due to a lack of data in that area. So you may just change the date windows and see if that actually resolves the CRS projection error. So loaded 12 time steps, and we'll just check with the print what we got. So we have data. That's good. So let's plot. Okay, so here we go. Let's see what we got here. So index 37 is out of bounds for access. Okay. So what we'll do, so there's a good example here. So it says, so a lot of this is just general error stuff, but the important bit of information is right down here. So it's an index error. So it says that index 37 is out of bounds for x is 0. So what we'll do is we'll just reduce this number until we get something. I'll bring it down to 30. It's still not enough. Let's take it down to 20. Still not. See, I think actually it said up here we've got 12. I'm just curious. Let's take it down to 15. Okay, let's take it down to 12. Let's see what it's got. Oh, no. 10. There we go. So it seems to like 10 for the final time step. Looks like we have a lot of cloud cover for that date. We can go back and actually, let's maybe change that and see what we got just real quick. Let's go to 20. Should have data up to 2021, but let's just go to 2020. And let's set our baseline comparison at say 2017. So we're just going to run back through this very quickly. The acquisition of the loading of the data takes just a moment. Thank you for your patience. So we've got 21 time steps now. And since we do, I'll go ahead and see if it'll take 20 here in the final time step. Looks like it did. So a little less cloud cover in the second date, some spotted cover in the first date, and it looks like we've got a big cloud here potentially in the second, but that'll give us something to work with. So we'll just keep running. It looks like I reran the same cell. Bear with me. And then this is an expanded cell here. So we'll do an NDVI analysis on this. Perfect. And I'll visualize that index with the NDVI index applied specifically. Also want to point out if there's, sometimes colorization can be important in just viewing in basic color more important features in the maps. And if you ever want to, you can actually look, you can search matplotlib CMap, and it'll give you kind of a range of functions that you can actually change this with. So you could do, there's all kinds of different colors. And if you just search that function, CMap options, matplotlib, you should be able to get a whole range of colorizations that you can apply in here. But right now we're doing just red, yellow, green. So you get some change there. It's good. So let's perform our hypothesis test. Great. So we're going to start testing for change, applying statistics. Let's make sure that it runs. Perfect. Okay. Great. So here's our statistically significant plots where we can see, looks like there's a little bit of change up here in the upper right-hand side, more so than the rest of the regions, but looks like we have a lot of spotted change in certain areas. Could be safe to assume that this area in the upper right-hand side could be due to human intervention. Let's just keep going down here.
At that place, there is quite a bit of mining in different spots along those places. So maybe that could contribute to the changes in those areas.
Could be. Could be interesting to run some more segmented slices along here, and this could be a great tool. If people wanted to put a little bit more effort in the notebook to actually apply Dask2 and run larger areas instead of having to go in manually and look at smaller regions, with limited processing power. So we see, it's pretty small percent of change, and we'll go ahead and write the cog and see what the actual output looks like. Actually, I think I need to delete these. So you can change the file name in the script there, right here where it says fname. You can change that and it'll actually output the different file name. Let's run that one more time. Okay. Take a peek over here. And there is our generated cog tiff of the area. But yes, nevertheless, I think overall, more dense areas of significant change are going to be higher indicators of, likely non-natural deforestation. I think our original example kind of showed some of the most change, whether or not that area in particular is due to human intervention, I do not know. But this does give a good premise for, actually, I think this is the Sierra Leone example, for at least engaging in the question of whether or not a certain area may be undergoing illegal mining or illegal logging operations, what have you. And in general, is just a great tool for seeing statistically significant changes in a given forested area. Are there any other examples? Any questions from the audience? Comments?
I have a question.
Yes.
My question is on the, thank you very much for your presentation. My question is on the time steps.
Okay.
Will you always need to decrease in order to make it clearer, or how do you go about changing it so that the image is clear?
So in terms of clarity, this is based on Landsat 8 data that has 30-meter resolution. So in terms of the clarity of a given area, with this particular product, this is as high a resolution as we get. With the time steps, so we have control over effectively the ranges of dates and the number of segments between dates that are actually being compared in the study. So let's see. If we go up just a little bit more, just want to run through a couple things. Let's see. I think it was here. So I just do want to point out, so when we're actually loading the data to the data cube, we see, it's loading, querying the lat long, the time, specific measurements, and this is where our resolution is projected, and this is in meters. And this is a product here, of course. And then as we go down here to the time step, this is, again, what is just being visualized in terms of the segments of time. So the higher, more time steps we have in here, also represented partially by this value that we did see earlier. This number did not necessarily correlate to the exact final time step that we could have here, but this gives us a broader statistical comparison between dates ultimately. So if you wanted higher resolutions, I think it could be possible to explore deforestation with, I'm trying to remember offhand. I think of the products, Ken, you may remember offhand. If you do, please interject. But I think of the products available offhand on Digital Earth Africa Sandbox. For most of the multispectral platforms, were limited to 30-meter resolution. That's not to say that there couldn't be higher resolution maps generated, but of the free data that we have, these are the maximum resolutions that we have. Does that answer your question?
Partially.
Okay.
You see, when you're doing the previous example, you were changing the time step to make so that you get the image. And I saw you either increased it or decreased it. So I didn't know in which situation would you need to increase or decrease.
So, okay. So to answer to that, it depends on the amount of data that is available. So for some date ranges, so if for example, I can show here. So for example, like if we go to say let's compare 2015, and we'll do Let's put our central date there. The time steps are relevant in comparing the amount of data that we have for a given area. So when we change that number, it's because certain areas that we're querying may have more temporal information than others. So I can show as we go down this notebook, let's look at the map, load the data. I think it's in the following. Let's see, let's load that. So right here, once we load the data, we see here that it loaded 4 time steps. Because the date range is so small, we only have 4 time steps. So if we go to run this right now, we're asking it to show us an initial time step of 2 and a final time step of 20. So it's looking for more data in time than is actually available. So we'll see here probably, so it says index 20 is out of bounds. So if we change this, let's say let's see what it does for 4 as referencing this, but we did see it didn't always like that.
Mm-hmm.
See, it still didn't like that, I think. There we go. So we see that this number is essentially, again, correlated ultimately to the amount of data that we have for a time range. So the more years that we have, the more time steps, the fewer years, the fewer time steps.
Okay. Thank you very much.
You're welcome. Any other questions?
I think this was a well-received webinar, as also we were trying to explain the dates for Kyrie in the chart that Landsat 8 is available from 2013.
Let's see. Yes, the baseline between the time range, why not 2012? Yes, so the reason for that is if we go to, we can view this in Explorer, digitalearthafrica.org, I believe, but we would pull it up here. This is a snippet of Explorer. This is the available data that we have. So all the notebooks for the vegetation change are being queried from Landsat 8. And Landsat 8 for Digital Earth Africa is only available from 2013 to 2021. So that's why we only queried back to 2013 in this case. And let me pull up Explorer as well so I can show everyone. And this is Explorer is a great tool for seeing what data is actually available for the given region. So anytime we go into a notebook, at the very, very, very top, it says what products are used. And if you want to see what data specifically might be relevant to your region of interest, we know in this case here it's Landsat 8. If we go to Explorer, what we can do is go to products. And this is actually all the products that are available on the platform. So what we can do is go to Landsat 8, for example, in this case. And it's going to show us some general information about the data here. Actually, I think it's at the top. If we, I believe we click this one, yes. And then, so this is the actual mapped visualization of the data sets available. So we do see here that there's 250,000 total data sets available across Africa for Landsat 8. And again, in the upper right here is where it's going to show the actual date ranges. And I think we can even go ahead and click. So for example, it even shows us in the little metadata there on the right, there's 2,600 data sets for October 2016. Actually, let's go all the way back to say 2013 there. We can click on that and it'll actually show us specifically where that data is available for that date. And if we let it run here, so we can see that there's actually some missing spots. So all these blue tiles here is a Landsat 8 tile available for that date for Landsat. And then these little open strips here are actually missing pieces of data. So this is actually a great example. If you're running through your notebook and you get a CRS error, it could be because you're in a date range where there's a missing tile in between here. So that is why we only go back to 2013 in this example.
I think this is a great presentation, and also I think I had a question from Kyria that she would like to do some like mangrove work with the GEOMET. Was that the question, Kyria?
Yeah, thank you, Dr. Ken, for this opportunity. Yeah, my question is, I want to extend the analysis of coastal erosion in Zanzibar, but I want to use a GEOMET. And I tried to run the GEOMET code from Sandbox using Landsat data, but unfortunately, it seems like there is an I can say they are not compatible, because when I try to look on the product, it seems there are some some records are missing there for the Landsat.
When was it that you tried to run the GEOMET product? How long ago?
I used the 2020 data, actually, 2020 years.
Okay, I do know that the GEOMET product specifically in Sandbox has been very recently made available. I think maybe in the last week or so. So if you've tried running that in roughly the last week, I don't know offhand, but we can certainly follow up on that and see why there may be an issue. If you did run it a little bit before that, it's likely because the data was not fully integrated into the Sandbox yet.
No. Yeah, it seems the data that's available for this GEOMET was Sentinel data.
It was the GeoMed, not the GeoMedian, the annual GeoMedian. Is that correct?
I tried for GEOMET and for GeoMedian, both.
Both, and they did not work.
Mm-hmm.
Interesting. Well, I would certainly, I'm sure you can follow up with Ken. Otherwise, please, I'm going to send here in the chat any questions or issues you have like that. Feel free to email us anytime at helpdesk@digitalearthafrica.org. I'm going to send this here, and we can work with you offline anytime to get that resolved for you.
Okay.
Actually, we can set a time.
I'm sorry, we don't have a better answer right now.
I'll set a time for us to connect with her after, because she has a class in the next 1 hour.
Great.
So that will
Thanks for your question.
Yeah. So thank you everyone for joining us. Stephen, Corey, did you have any comments, or you wish to present on your presentation next week?
I'm okay. Thanks for the session. I don't think I have anything to say. Probably next week. I'm not very sure. If I have anything, I'll let you know.
Thank you so much. Otherwise,
Thank
Stella, thank you. We received your message. Edwin Edwin has joined us from Water Resources Commission in Ghana, working closely with Eric Mwala. And also everybody's on board. Since we have this classroom environment, you can enable your camera just to see how we are all doing. Good.